Hello aspirants, this question is from GATE 2019 Mechanical Engineering paper set 2, question number 32. A slender uniform rigid bar of mass m is hinged at point O. This is point O and supported by two springs with stiffnesses 3K and K and a damper with damping coefficient C as shown in the figure. For the system to be critically damped, the ratio C by under root Km should be. So among these four options, we have to determine what is the value of the ratio C upon under root Km. We'll start by making some observations in the given information and in the diagram. So from the given information, we know that as the rod has its mass distributed along the length L, mass is not actually lumped at a single point. So this is not a lumped mass system, but it is a distributed mass system. The second observation that we can make is number of degrees of freedom, NDOF, in the whole system is 1. That is, when this rigid bar will rotate about point O. That is nothing but the 1 degree of freedom of the system. And so that degree of freedom of the system is nothing but theta. Now as the mass is not lumped at a single point, the system is of the type generalized single degree of freedom system. And the generalized coordinate in this system, there is only one generalized coordinate, that is theta. Equation of motion for such generalized single degree of freedom systems is given as m star, which will represent a mass equivalent. It will not directly be the mass, but it will be a mass equivalent. Similarly, c star theta dot and k star theta, both c star and k star being the equivalents of damping and stiffness. There is no external load on the system that is given, hence we have put the right hand side to be 0. In the second part of this solution, let's draw a free body diagram for the given system. In this diagram, we can see that the rigid bar has rotated by a small angle theta. Theta is a small angle. I have just drawn the exaggerated figure for representation purpose. Vertical displacement at points where spring and dampers are attached are given to be delta 1, delta 2 and delta 3. Now we need to mark the forces in the spring and the damper. This spring will be compressed because the bar is going up and the compression is shown towards the bar or towards the joint. The damper is going to be tensed, so the tension is shown away from the joint. Same here, the spring is going to be tensed, bar is coming down, so the spring will be in tension. That tension is shown away from the joint. We can mark them as F1, F2 and F3. Now we need to write the equilibrium equation of this system. We can clearly see theta is the angular displacement of the bar. So moment about O will be 0. For the system to be in equilibrium, the equilibrium equation is moment about O is equal to 0. By considering all these forces F1, F2, F3 and in addition moment of inertia of the bar, that is also a force in the system. So we will also have to consider the moment of inertia of the bar about point O and then add all the moments, equate it to 0. That's what is this equilibrium equation. Summation m about point O is equal to 0. You can pause the video and try solving this question and find the answer yourself. And then you can match with the answer in the video. So let's continue with the solution. Force on the bar due to its inertia will be m theta double dot. But the moment of this force will be computed by I theta double dot, that is moment of inertia into acceleration. So that is the first moment, I theta double dot, plus the second moment will be F1 into the distance from point O, that is F1 into L by 4, plus F2 into the distance here is L by 4 again. F1 is creating an anticlockwise moment, so it is positive. F2 is also creating an anticlockwise moment, it's also positive, plus moment due to F3 is also anticlockwise, that is also positive. F3 into, here the distance is this distance L by 4 plus this distance L by 2. So it is L by 4 plus L by 2 is equal to 0. Now we need to find all these components I, F1, F2, F3. Let's find out those. I of the bar is equal to moment of inertia about center. We don't want the moment of inertia about center, we want it about point O. So it is equal to moment of inertia about center plus mass of the bar into distance of point O from the center. So center of the bar was here and distance from point O is nothing but L by 4. So we will take here L by 4 whole square. This is by parallel axis theorem, which is equal to moment of inertia of a bar about center is given as ml square by 12 plus ml square by 60, which is nothing but 7 ml square by 48. This is our first value, I of bar. Now second thing, let's calculate F1. Force in spring F1 can be given as stiffness of the spring 3 times K into the compression of the spring. Compression of the spring is equal to the displacement of this point of the bar, that is delta 1. So we'll write 3K into delta 1. But we need to find delta 1. Now delta 1 can be found just from this triangle because as theta is small, so we can write delta 1 is equal to theta into L by 4. Therefore, we get F1 is equal to 3K L by 4 into theta. Similarly, you can compute F2, which is equal to C into delta 2 dot, velocity of the bar at that point. So it is nothing but time derivative of delta 2. And by linear relationship, delta 2 dot is equal to theta dot into the distance, that is nothing but L by 4. So F2 we get to be C into L by 4 theta dot. In same lines, F3 can be found as K into delta 3, and delta 3 is nothing but theta into the distance from point O. Distance from point O is the summation L by 4 plus L by 2, which is nothing but 3L by 4. Hence, F3 is equal to 3K L by 4 into theta. So we have all our values. We have I value 7 ml square by 48, F1, F2 and F3. We will use these values and substitute in the equilibrium equation. Let's see what we get. So we have all these values. After substituting I, F1, F2 and F3. I just wrote damping first and then the stiffness terms. By comparing this equilibrium equation with the equation of motion, the one with the m star, c star, k star, we will just write the coefficient of theta double dot, theta dot and theta together. So we can write the values of m star, c star and k star. Now further, we are being given that the system is critically damped, and for that system we have to find out C upon under root Km. They have not asked to find out C star upon root K star M star. This value is completely different from this value that they have asked us to find out. So find out C upon under root Km. Now we know that damping ratio zeta is equal to damping constant, in this case C star, upon critical damping. For generalized single degree of freedom system, critical damping is written as 2m star omega n. Omega n is the natural frequency of the system, which is given by root over. For generalized system, it is k star upon m star. If you want to try, you can pause the video and try to substitute omega n and then find out C upon root Km ratio for critically damped system. Notice that it is a critical damped system. Put the value of zeta accordingly. So moving ahead with the solution, putting 1 is equal to C star upon 2m star From here, omega n is root over k star upon m star, which is equal to c star upon 2. With root m star, we can cancel one of the root m star. We get 2 root k star m star. The only step remaining is to substitute c star, k star and m star from here. After putting all these values, we get this term is equal to 1, and after simplifying, we get c upon under root of 16 into 7 into km is equal to 1. So in order to find out c upon root km, let's keep it on left hand side and take all other terms on the right hand side, which is equal to under root 16 into 7. Just by simplifying, we get root 16 is 4, so 4 root 7. Our answer is option D. To study generalized single degree of freedom systems in detail, you can refer to the NPTEL video, Module 1, Lecture 17, Generalized Single Degree of Freedom Systems, Equations of Motion, in the course Structural Dynamics by Dr. Banerjee, Department of Civil Engineering from IIT Bombay. I hope you understood this solution. Have a great day. Thank you.